In this video, we are going to learn on how to construct the Born-Haber cycle for a simple ionic solid by using the energy cycle. For the energy level diagram, I will explain it in another video. Okay, and also we are going to calculate the enthalpy changes using the Born-Haber cycle. So for the Born-Haber cycle, just remember this cycle where we want to produce the ionic solid. Okay, so here we have the ionic solid. Okay, so the formation of the ionic solid, okay, it comes from its element. Okay, so here actually is the enthalpy of formation definition. So we are going to use the enthalpy of formation definition, which is the formation of the ionic solid. It comes from the elements. All right, so I always start with this first. Our ionic solid comes from element, and then from elements, okay, we are going to change it into gaseous atom. Okay, the gaseous atom. So if you notice here, the changes from the elements to the gaseous atom, actually this is the enthalpy of atomization. Okay, the enthalpy of atomization, if you still remember the definition, heat absorbed when 1 mole of gaseous atom is formed from its element. So we have the enthalpy of atomization, and then after we change it into the gaseous atom, we are going to change it into gaseous ion. Okay, gaseous ion. Okay, for the gaseous ion, air is divided into two ions, which is the positively charged ions and the negatively charged ion. Since the ionic solid comes from metal and non-metal, right? So the positively charged ion will comes from the metal, while the negatively charged ion comes from the non-metal. Okay, so to form a gaseous ion, okay, from the gaseous atom, if you still remember, the formation of the positively charged ion, okay, comes from the ionization energy, while the negatively charged ion that comes from the gaseous atom is an electron affinity. And last but not least, we have the conversion of the gaseous ion into the ionic solid. So this one actually the lattice energy. Right, so we have the lattice energy, which is from the gaseous ion to form the ionic solid. The magnitude of the lattice energy here, the process is always exothermic. It is different from the dissolution process. For the dissolution process, the lattice energy that we use is in endothermic process. Okay, but here in the Born-Haber cycle, the lattice energy that we got here is always negative sign. Okay, because we are going to form the ionic solid from its gaseous ions. So to construct the Born-Haber cycle for the lithium chloride, okay, so the formation of the lithium chloride solid, so lithium is metal in group 1, okay, so chlorine is a non-metal from group 11. So the formula for the lithium chloride is LiCl solid. So this is our ionic solid. So to use the energy cycle diagram, I always start with my ionic solid first, and then I'll go with the elements. Okay, since we have two atoms here, so the lithium chloride must comes from two elements, which is, okay, the metals is lithium solid, okay, plus with chlorine, the elements of chlorine in their most stable state is the Cl2 gas. Okay, and then balance the equation. Okay, so since we have 1 mole of the lithium chloride here, okay, this one is the enthalpy of formation. Okay, enthalpy of formation of the lithium chloride, right? So here, the 1 mole of the lithium chloride formed here, you cannot touch its coefficient. It must be in 1 mole. So to balance it, you can adjust these two. So since here we have one lithium is already balanced, but here we have 1 chlorine, but here we got 2 chlorine. So we have to times it with 1/2. Now we will get 1 chlorine on the left side and also on the right side. Okay, So after you got your elements, we are going to change it into the atoms gas. Okay, where this one we are going to apply the atomization. Okay, enthalpy of atomization. Okay, for lithium solid. Okay, it will becomes a lithium gas. And then for the chlorine gas, okay, Cl2, okay, it will become a Cl gas. Okay, so since here 1 over 2 times 2, yes, we will get a Cl gas. Okay, and then after we convert it into atoms, so let me just label it as atomization. Okay, delta H atomization. This one is also the delta H of atomization for chlorine, for lithium. All right. So after you got your gaseous atom, you are going to convert it into gaseous ion. So since here the ionic solid of lithium chloride comes from lithium plus ion and Cl minus ion. Okay, so lithium gas will become lithium plus gas. Okay, because it is metal. Okay, so metal, we are going to apply an ionization energy of lithium. Okay, and then for non-metal, right, for non-metal, Cl gas will become Cl minus gas. So for non-metal, we are going to apply the electron affinity of chlorine. Okay, and then last but not least, from our gaseous ion, which is Li plus gas and Cl minus gas, okay, we add this together, it will form, okay, we are going to put our arrow into the lithium chloride solid. Okay, so ion gas will goes to the ionic solid. So this one is the lattice energy, right? The lattice energy. So this is our cycle. Okay, so since we have two atomization here, okay, so it's quite long if you want to write it down as atomization. What you can do is change it into numbers. Okay, so you can change it into numbers. Okay, delta H1, delta H2. Or here also you can change it into delta H. Okay, so just leave the formation and lattice on its own label. Okay, so delta H1, delta H2, delta H3, and delta H4. Okay, so since here its enthalpy is given in a form of equation, okay, so we are going to match it with our cycles. Okay, so we have first lithium solid to lithium gas, lithium solid to lithium gas. So actually this one is enthalpy of atomization of lithium, which is the value positive 159 kilojoule. So since here, even though here we got kilojoule per moles, in the cycle just leave it in kilojoule. Okay, so we have the atomization of lithium and then lithium gas to lithium plus gas. Okay, so we have lithium gas to lithium plus gas. So this one is the ionization energy of lithium, which is positive 520 kilojoules. Okay. The third enthalpy is half Cl2 gas to Cl gas. So half Cl2 gas to Cl gas. Okay, the value is positive 121 kilojoules. Okay, and then we have Cl gas to Cl minus gas. Okay, the enthalpy is negative 364 kilojoules. Okay, and then last but not least, we have lithium solid plus half Cl2 gas produce lithium chloride. Okay, so this is the enthalpy of formation actually. Okay, so this one is electron affinity, this one is enthalpy of atomization of chlorine. Okay, so the value is negative 409 kilojoule. Okay, by applying the Hess's law, okay, again the Born-Haber cycle is also the application of the Hess's law. Okay, so the delta H formation, right, so delta H formation of the lithium chloride is equals to delta H1 plus delta H2 plus delta H3 plus delta H4 plus delta H lattice. Okay, so this one we want to find its value. Okay, so if you look at here, why I said it is an application of the Hess's law, because this one is one step, okay, and then we have another root, okay, that will give us several steps. Okay, so the summation, the enthalpy of formation is equals to the summation of this enthalpy. Okay, so substitute the value. Negative 409 equals to 159 plus 520 plus 121 plus negative 364 plus delta H lattice, and then you can find the value of the delta H lattice for the lithium chloride. Okay, and then your answer, your final units should be in kilojoules per mole, because we take its definition. Okay, energy released when 1 moles of ionic solid compound is formed from its gaseous ion. So this is it, the energy cycle diagram.